not just your infotainment system. The brakes are probably fly-by-wire. The transmission is going to have its own computer. There's going to be another one orchestrating everything. It's a data center on wheels. So inspired by a hackathon I'd run a few months earlier, we decided to build our own miniature self-driving car, because JFrog wouldn't buy us like a real car to maybe potentially brick. It's quite an investment. So I'll spare you the details on how it worked, since this isn't really the talk for it, but we took updates on the car from something that could take like hours and required physically flashing the boards in the car, like Jaguar had to when they issued a widespread recall for the F-Pace because of a software problem with the braking system, to like 35 seconds for an application update and 5 to 10 minutes for a full firmware update, both of them without interrupting the user. They could happen without the user's knowledge or consent. We wouldn't advise that because that's shady, but in theory, you could do it. And it relied on like us gluing together a ton of tools, both JFrogs and some open source tools like Yocto and Mender and K3S. From a technical perspective, it was really, really cool. It was impressive. It was revolutionary, but it also looked really cool. So we had a racing simulator set up in the middle of a large track in this hotel, complete with pedals, a wheel, a screen, this racing chair we found on Amazon. And that's me making sure everything is set up before the conference actually opened. We allowed people to interact with it in one of two ways. We would let actual randos off of the conference floor write and push code to that car, or you could drive the car while someone else updated it. And what we found was that people really liked to mess with the driver. Like, people always wanted to make the steering super loose or like flip the screen vertically or something. It was fun. But while this demo, part of the demo at least, wasn't really revolutionary from a technical standpoint, it was super fun to build, still fairly complicated. And this is something that you could build a version of this yourself, and it would allow you to dip your toes into a lot of really interesting types of technology, from hardware to computer vision. And this part of the demo was largely my baby, so here's how I managed to do it. So it started out as a very basic self-driving miniature car. It was a donkey car to begin with. If you aren't familiar with those, I wasn't before I heard about them at another Python meetup. It's a miniature RC car that's been modified with a Raspberry Pi and a camera. The library that enables it to do its thing is called Donkey, hence donkey cars. And in its most basic form, you can build one for like $250 in parts and a couple hours of your time. Like, really the most expensive thing is getting the car itself. And once everything's set up, you record 10 laps or so on a track marked with brightly colored masking tape or paper on a dark floor, like really anything that creates a lot of contrast, and dump the recorded images and steering data back to your computer and train a model for it. They provide a pretty decent CLI for this, so you don't have to like actually super understand how machine learning works to use it. And they're pretty fun. A whole community exists around like improving and modifying and racing them when, you know, in the before times when we could still be around other people. Ours was a little bit beefier than the standard donkey car, since we were forcing it to do more work than it was really built for. But physically, the only modification we made to ours is, instead of using like a Raspberry Pi 3B, we used a Raspberry Pi 3B Plus in a compute module, and that's what's pictured here. So we wanted it to be cooler though, and I'm kind of extra, so we wanted to set up where the person participating in the demo as the driver felt like they were playing a racing game or actually driving a car, close as we could get. And this meant we needed to be able to control the steering with an actual wheel and throttle and brake pedals. So we assumed from the beginning that modifying the donkey library pretty heavily was going to be required. And we also didn't want to mess with manually dumping the images and steering data during a live demo. Like, that's going to interrupt people. It's slow. It's kind of clunky. So we decided we were going to figure out how to automate that and move the work to GCP. I also wanted a TV screen in front of the driver's seat so that they drove using the feed from the car's actual camera. And since things weren't like already complicated enough, we decided to throw in some computer vision and put a green screen around the track. That one was actually an example of feature creep. It was a request from like the VP of Biz Dev. And I was like, I'd been working at JFrog for only a couple of months and I was really desperate for them to like me. So I was just like, yeah, sure, I can totally, there's room for that. There was, but you know, I learned a valuable lesson about setting boundaries about expectations there. So the donkey car is easiest to control with a web app on your phone. That's actually what it wants you to do by default. And that wasn't really interactive enough for us. And it didn't give us the like actually driving feeling we were going for. The donkey library calls its various moving pieces parts, and it lets you add additional parts. It's not super well documented how to do that, but you can. It supports it. It did include experimental support for a number of different physical controllers, and those have been fleshed out a little bit more since then, though I haven't messed with them myself. But the one for a race wheel didn't really work the way we wanted it to. And we were using a Logitech G29 Driving Force, which is a really popular racing simulator controller that supports PlayStation, USB on a PC, and Xbox. And it just didn't seem to want to behave. We couldn't get the pedal feedback at all. So we just wrote our own, and it wasn't as complicated as it seemed like it was going to be at first. The race wheel part relied on ZMQ and the Python bindings for it, PyZMQ. It works by just requesting the current values from the racing wheel and pedals through a ZMQ proxy running on the machine that the racing wheel is plugged into. In our case, we had an Intel NUC hidden underneath the driver's seat, and that NUC was basically deadlifting the whole demo, honestly. So once the part is added, swapping out the standard controller is really, really easy. You just SSH into your Raspberry Pi on the car, open up the manage.py and VI or whatever, I don't remember what's installed on it by default, and add it as the controller instead of the joystick controller object. You'll see joystick controller in there exactly one time, just swap it out. So in our case, it was wheel instead of joystick controller. To make the driving experience feel a little bit more like an actual car, we do some pre-processing on the values from the race wheel before they get sent to the car. The standard library doesn't really account for things like throttle scale or steering veer. So we have these two helper functions doing some of that math for us before sending values to the car. Otherwise, the throttle feels really awkward and super touchy. Like if you just exist, if you breathe on the pedal, the car is going to go screaming off into the distance, and it doesn't understand like a throttle curve at all. So this fixes some of that for us. We also allowed for customization of force feedback on the steering wheel to make it feel like easier or harder to turn. Like if you've ever driven an old car with like a super loose steering wheel and you have to turn the whole wheel, like feels like 9 times to make a left-hand turn, you could go from that to like actively a struggle to turn the steering wheel. That was a really common thing for people to want to do to mess with the driver. Usually it was actually a marketing guy in the developer's seat, like trying to push something, and then an actual engineer in the driver's seat being bamboozled with bad steering. So that was super entertaining for them. But back to the point, the track is circular, so obviously the driver needs a way to see like where the car is. They don't have eyes on the back of their head. They need to know like when to turn the wheel, right? So to accommodate this, the NUC under the driver's seat does a little bit more work than we originally expected. What we ended up with is a SANIC web server doing most of the heavy lifting for the back end. I will admit that I picked that because I thought the name was funny because of the like weird Sonic meme, and a Vue.js app for the front end. Instead of storing all the training data in a directory on the Pi, we reroute each frame and the associated steering data through the ZMQ proxy under another topic. An async function subscribes to that topic and a few other ones that are handling like parts of our CI/CD pipeline and the race wheel data and some other things required for updates. And according to whatever the current customization settings are in the config file, it processes the data and sends it where it needs to go. So at bare minimum, the Vue.js app on the driver screen is going to display the raw camera data from the car, the current build, and buttons to record or upload new training data. I'm not going to show you the code for this part of it because it is possibly the single ugliest Vue.js I have ever written, and it was never supposed to see the light of day. I'm also, like, I know JavaScript, but I would not call myself a JavaScript developer. So it's like some turbo embarrassing code. But it worked by using JavaScript bindings for OpenCV. I was shocked to find that that even existed. And an open WebSocket to just continually redraw the images from the camera topic on our ZMQ proxy to a canvas element. That was quick enough that there wasn't much lag between what the driver's seeing in the camera. It was like 100 milliseconds or so. So it was actually still really easy to drive it off of that feed. If you were like hugging the wall really tight, that's enough time for you to like screw up and veer into the wall because you didn't turn quickly enough. But otherwise, it was pretty much a non-issue. So at this point, the interactive part of the demo functions, but it's not as flashy as we want it to be. The driver doesn't have any nice scenery to look at. They're just going to be staring at people's feet, standing around the edge of the racetrack, and that sucks. So let's stand a bunch of green poster board around the perimeter of the track and write the green screen that you can see in that picture where we are currently driving through the desert. So if you've never done computer vision before, this was my first time. I learned it. I mean, I would hesitate to say that I understand computer vision. I understand how to make a green screen, but this was the first time I dealt with computer vision at all. So in its simplest form, a script like this works by using OpenCV again to just read in a frame, convert it from RGB to HSV, which is hue saturation value, and create a mask out of any parts of the image that fall within a range of HSV values that you define, a high and a low. You then use that mask to crop the background image you want and replace the corresponding spaces in the original image. To get the edges closer to perfect, you can like kind of erode and dilate the mask and then run a blur and a smooth as well. Because there's like a little bit of guesswork involved in finding the perfect high and low ends of your range. So you'll end up with like green bleeding into the edge or something like that. And the erosion and dilation helps kind of like fuzz the edges a little bit, makes it look a little bit neater. Then you just convert it to RGB and return the frame. And you've made a green screen. I am happy to like publicly post the whole code for this green screen somewhere because it's like, that's not proprietary, it's a green screen. However, what we discovered is that we couldn't leave the image static. It had to appear to move as somebody was driving, because if it was static, it was actually really disorienting and super, super hard to focus. So to do that, we did some more magic math using the current angle of the steering wheel and the starting X and Y coordinates to calculate how far we needed to move the area to crop for the background from one frame to the next. We did also have a scale variable involved to increase or decrease the speed of the pan, which could make it feel like the driver was going faster or slower, though we didn't really use that much. We found that like an even 5 was pretty perfect to make it feel like you're going like, 45, 50 miles an hour through the English countryside. We did also allow for stuff like image filters and different backgrounds to be applied as some of the like updates people were pushing. These also took place within the green screen script, like just changing the background we were sending in or like inverting the colors or flipping the image vertically. But those are like built-in functions for CV2, the Python bindings for OpenCV. So there's no like real magic or hard work involved there, but I'm happy to share those functions as well. For the training, that was actually relatively low effort. Once we got over some hurdles related to TensorFlow on GCP, this was pretty easy since we already had the images and the steering data coming through our ZMQ proxy. So we just passed that data along to a tub writer utility that was also running on the NUC to collate the data and then chuck it up to GCP to train there. Then whenever a new model was available, the driver's UI would update to reflect that availability and allow the user to use that instead of driving the car manually. Most people wanted to drive the car manually, but some people really wanted to see it drive itself. They didn't believe that it could do it. We did pre-train it with a coworker who was uncommonly good at driving this thing. So it would go for like 30 minutes without, I don't know, getting distracted and running into a barrier. However, this was still pretty slow, which I don't know how fast it'll ever be. It still took like up to 10 minutes to get all of the data, get all of the like the tub together, chuck it to GCP, train it, and get it back on the car. But it was way faster than the manual way, which involves, you know, stopping the car, SSHing into it, sending the files back to your laptop, training it locally on a laptop instead of on a dedicated GCP server, and then sending it back. Because that's like a 20, maybe 30-minute thing longer if you have an older laptop. So 10 minutes and we don't really have to touch it. It's just a literal button on the steering wheel that the driver clicks. It's pretty good. We'll take it, you know? So that's how the flashy parts worked. Like I said, it's not revolutionary, but it is super fun to build, and it's a really good opportunity to teach yourself about hardware and machine learning, message queues if you've never used them. I had never used them before this, and I thought it was like the dopest shit in the world. And computer vision all in one project. I can't publish the entire code base for this demo, but if you're interested in trying part or all of this system for yourself, I am happy to send you more complete versions of what I talked about here and the code samples I showed. I'm happy to give you the whole file for that. It's fine. And answer questions personally. That's also something I'm totally down for. So again, my name is Kat Cosgrove, and you can get a hold of me on Twitter at Dixie3Flatline. We are also raffling away, just for y'all, not for every meetup we do, 2 Circuit Playground Expresses and 2 JFrog t-shirts at the bit.ly link here. Oh, you already have them. Okay, cool, yeah. So if you've ever seen a Circuit Playground Express before, it is a small circuit board made by Adafruit with a ring of their NeoPixel LEDs around the outside. They are super bright. It's going to be like uncomfortable to look at them directly, and a load of different kinds of sensors on board. It's intended for teaching hardware hacking, but there are some practical applications for it. Like recently, I saw a woman use one to build an automatic touchless countdown timer for washing her hands, which I thought was super cute. And it's done in a flavor of Python called CircuitPython. It's just an open source derivative of MicroPython, and it's designed for use on microcontrollers. It's got a lot of hardware bindings built in that aren't included in the standard Python library, so it's super, super easy to get up and running with it. It's really fun. It's good if you don't know Python at all, or if you're a beginner, or if you're an expert. It's cool if you're working on microcontrollers and you don't want to write C. So that's it. I hope you enjoyed, and I will take any questions if we have time for it. That's up to the organizer, I think. So happy to take questions.
I'll ask a question. Like, first of all, message queues, also awesome.
Yeah.
Very cool. Was sort of why 0MQ as opposed to anything else? Was that sort of in the tutorial, or was that something like, was that just a convenient way to get like, did you select that and that was just a convenient way to get data off of the car? Or like, I guess, why a message queue as opposed to something else?
A message queue is super lightweight and crazy fast. So That's it. It's just, it was faster than building an API. Like HTTP requests take an eternity. So we were in a situation where like, if the driver is going to have to know how to drive the car based on the video feed coming from the car itself, and there's going to be an intermediary, HTTP calls take too long. Like 300 milliseconds of lag is enough to make the car undrivable. And we were in a spot where we had like between 40 and 100 milliseconds of lag, which was doable. You know, it's noticeable, but as long as you don't like get distracted and look at the actual car out of the corner of your eye, it's totally fine. I drove it around the office and harassed coworkers with it. But yeah, it's just a message queue is just faster. I had never used one before. I didn't know really what they were. And my feeling now is that maybe sometimes we overuse REST APIs, and there are a lot of things that would be better suited to a message queue because it is faster and simpler and less dramatic.
Thank you.
Yeah.
I didn't want to monopolize the questions. If anybody else has a question, please.
I won't be offended if they don't.
All right.
I have a comment, and it's totally my bad, Kat. I put the wrong bit.ly on the slide, so this is the one I asked to incorporate. But in the chat box is the correct address, and basically just add the word JFrog at the end of SD Python, and you won't get that nasty looking 404 that a lot of you have already commented on. So it's in the chat box, and at the end of the evening, you have a little while between now and next talk and so forth, and the end of the program. I'll randomly select the winners for these prizes tonight. So just wanted to make sure everyone knew.
Well, thank you very much. Thank you.
If I might have, David, I just wanted to make a comment on those queues. So a couple of years ago, when we were actually starting to design one of the new projects that we have at our company, we were evaluating different messaging systems, and one of the requirements was basically making it very lightweight. Unfortunately, none of the actual commercial or readily available open source ones were able to, suffice our requirement, because yeah, they might be fast, but tons of requirements or importing libraries. So we end up actually implementing our own routing mechanism using queues for for within threads, and MQs for multiprocessing. Is a very rudimentary, but that allows to, as you mentioned, it's pretty strong, pretty fast, and very reliable. So yeah, kudos. I also, +1 for queues.
That's cool though. I don't think we should reinvent the wheel unless we can avoid it, but sometimes it's really fun to reinvent the wheel just for giggles.
I agree. Sometimes the wheel needs reinventing.
It's true. Sometimes the wheel sucks.
Yeah.
And sometimes reinventing the wheel is a good way to teach yourself something too.
That's true. That's true. I always learn a new language by rebuilding like the same crappy CRUD app like repeatedly. That's how I start learning a new language. Same CRUD app again.